Within this video, my plan is to explore some new ideas within Chapter 3 and also have it serve as review for some previous topics that we've already discussed. Within the scheme here of moving through Chapter 3, this particular video explores ideas pertaining to Avogadro's number. When I look at the different objectives and topics within this class and their degree of difficulty, we're going to be looking at examples where we convert between mole, mass, and number of particles. I'm putting in bold mole and mass because that's a skill that we're going to be seeing again and again. That's used for stoichiometry problems and other tasks within this class as well. So we definitely want to be able to convert between mole and mass. Learning objectives for the start of Chapter 3. An early one is we want to be able to calculate formula weights. That's in section 3.3. What we would call rust is given the formula Fe2O3. What I'd like you to do is stop the video and see if you can name this compound correctly. Use the periodic table to determine the formula weight and calculate what percentage of the total mass is coming from the iron. Stop the video, give that a try. Here would be my answers. So Fe2O3 is an ionic compound. Oxygen is 2-. So I'd have to designate the charge for the iron. So I would say it's iron 3 oxide. The formula weight I obtained by adding up the numbers from the periodic table. And how much of Fe2O3 is iron? About 70% is coming from the iron. Units there are AMU. That stands for atomic mass unit. Within this video, we'll explore a little bit more of what that means. When we looked at the subatomic particles, proton, neutron, and electron, we described them as having a particular charge and a particular mass. The charge, those were different multiples of the fundamental amount of charge, 1.602 times 10 to the minus 19th coulombs. So when we say something is +1 or -1, it would be in increments of that fundamental charge. An electron at -1 has a negative 1.602 times 10 to the minus 19th coulombs for its charge. Very small amount. If we look over there, so before we move on here, if that's the fundamental charge for an electron, how is that determined experimentally? That's what the particular value is. How is that determined? Thinking back to Chapter 2, we want to be able to discuss the scientist, the experiment, and the significance of the experiment. So pause the video here. What can you recall about the determination for the fundamental charge of the electron? So I hope that you associated that with Millikan's oil drop experiment. That's a scientist. The significance of his experiment was he was able to determine the charge of the electron. If you recall, we had a description for the experiment and the data analysis. I want you to pause the video again. To be able to understand the experiment, I think you should be able to describe and explain any of these features that are shown here. I'm not asking you to write an essay about every one, but which of these are you confident that you're able to explain? Which of these do you still have gaps in your understanding? Similarly for the data analysis. Recall those ideas. What was going on within the data analysis? So if we look at the mass, we see that the units there are AMU. So an AMU must be a small amount because we're talking about the mass for a individual proton or an individual neutron. If it's given a value of 1.0073, an AMU must be a very small mass. This brings up the idea of the atomic scale. So it points out that initially, scientists were able to determine the relative mass of one element compared to another. So if they were looking at 100 grams of water, they were able to find the proportion that was coming from hydrogen and the proportion that was coming from oxygen. Goes on to say that once scientists understood the formula for water, they would get greater insight into the relative mass for hydrogen and oxygen compared to each other. That idea of determining the formula for water is having 2 hydrogen atoms for each 1 oxygen atom. Insights for that would come in this era from an experiment like the electrolysis of water. Sending electricity into water, you find that you produce in this chamber oxygen gas and in this chamber hydrogen gas. Showing them as different sizes because the volumes were different. You've got 2 volumes of hydrogen gas for every 1 volume of oxygen gas. That's how they had insights into the formula here. So the notion that the water molecule has 2 hydrogen atoms for each 1 oxygen atom, I agree with that. Looking more closely, a reaction to form water, you could combine hydrogen gas and oxygen gas to form water molecules. This would be the opposite of the electrolysis experiment. So in this era, when they were trying to think about it, look at it this way. So we've got, each of these is, the volume is a liter. We've got 2 liters of hydrogen atoms, 1 liter of oxygen atom to produce 1 liter of H2O. This is how Dalton thought about it. If water has the formula of H2O, I would combine 2 liters of hydrogen atoms plus 1 liter of oxygen atoms to form 1 liter of H2O. For Dalton, that would be describing this reaction of hydrogen gas and oxygen gas combining to form water molecules. Is that what you think takes place at the particle level? Do you agree with the description that Dalton is summarizing there? Or do you have something else that you think is going on? What's taking place at the particle level here for the reaction of hydrogen gas and oxygen gas to form water molecules? This is the actual experimental result. If you combine 2 volumes of hydrogen and 1 volume of oxygen, you find that you get 2 volumes of H2O. Dalton is pointing out this is a contradiction. Let's just look here if we're counting up the oxygen atoms. In this box, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygen atoms. And then over here, if the formula is H2O, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dalton says this is crazy. How do we make even more oxygen atoms? We've doubled the amount. Similarly, we would have had to double the amount of hydrogen. So is this what's taking place at the particle level? Pause again. Look back with your previous explanation. If your previous explanation agreed with Dalton's description, then you need to revise it because it doesn't fit the experimental result. Let's see what the formula would be. So this would be a balanced chemical formula, and this would be a particle level description. Notice a key difference right here. Instead of saying we had hydrogen atoms, we had hydrogen molecules and oxygen molecules. Now if you add up the particles, it works out. If you were to take the oxygen that was O2 molecules, separate them out, you haven't increased or decreased the number of oxygen atoms. You've just separated them from the molecule, and now you formed a new molecule within the H2O. This is what Avogadro proposed. So this was in 1811. He proposed that the fundamental particles for the hydrogen and oxygen were diatomic molecules, not the individual atoms. And this then makes the reaction work at the particle level. So if you could go back in time and let's say you proposed this in 1810, you scooped it before Avogadro, how would that be received? Not well. Dalton was a scientist with greater clout in this era, and he disagreed with the idea. And so the notion of diatomic molecules was rejected for about 50 years. It wasn't until 1860 when it was revisited once again that this idea of diatomic molecules was actually accepted by chemists. Goes on then to discuss more about the mass. Describes how we can now determine the mass of individual atoms with a very high degree of accuracy. They have to have a really small mass value, and sure enough they do. 10 to the minus 24th grams, 10 to the minus 23rd grams, so a very small amount for an individual atom. AMU, that's to have a scale where we're going to define the mass of the carbon-12 isotope of carbon to have a value of exactly 12 AMU. And then we can look at the other particles relative to that. So our scale for the AMU is defining a value of 12 for this isotope of carbon-12. Now, when I see isotope of carbon-12, what comes to mind is mass spectrometer. That's what we explored a little bit when we were thinking about isotopes. Here's the analysis if you test hydrogen. So with hydrogen, we see a peak at a value of 1, a peak of value of 2, and this is in M to Z ratio. That's a mass to charge ratio where the scale is defined where carbon-12 would be precisely 12 AMU. So if we look at this, do you think that they're testing hydrogen atoms or are they testing hydrogen molecules? Here I show the experimental data if you test chlorine, if you test hydrogen chloride. Pause the video, use this as an opportunity to explain the output of a mass spectrometer. What do the different peaks represent here in a sample of chlorine? Can you explain the spectrum for the sample of chlorine? How about HCl? Look at the particular values on the x-axis and see if you can share some ideas. How is the mass spectrometer working and what's giving rise to these particular peaks? Moving on to the last portion in 3.4, the concept of Avogadro's number. So a single molecule has a very small mass expressed here in terms of AMU, and recall that's in relation to carbon-12 having a precise value of 12 AMU. In the lab, we're not going to measure things out in AMU. We need to scale it to get to a everyday size. We scale it up by using Avogadro's number. So if we have one molecule, it would have this mass. If instead of 1, we have 6.02 times 10 to the 23rd, a huge number of them, that turns the AMU value into a gram value. So we're almost always going to be over here in the molar amounts. We have a mole's worth when we have Avogadro's number's worth. So I always find this interesting. The value is 6.02 times 10 to the 23rd. How in the world do they measure that? Did they measure it? Here's a influential paper on the subject, on the elementary electrical charge and Avogadro's constant. So this is the actual article from the scientist, someone we've heard before, Millikan. Is this the same Millikan with the oil drop experiment? It is. Notice he goes on to talk about the oil drop method. What does the oil drop method have to do with Avogadro's number? We're going to see it brings together two ideas that we've been talking about within this video: electrolysis and the oil drop experiment. So within electrolysis, we're using electricity as a reactant. We could add electricity to sodium ions to make sodium metal, to magnesium ions to make magnesium metal. So electricity is a reactant. It was measured that the charge for 1 mole of electrons had a certain amount of charge attached to it. That was called a Faraday. So from electrolysis experiments, it was found that it took 96,485 coulombs of charge to equal 1 mole of electrons. They didn't know how many particles that consisted of, but they could be able to determine the number of moles and the corresponding amount of charge. Now, within Millikan's experiment, we now know the charge for 1 electron. So we have insights from electrolysis, which tells us a mole amount, and now we have the charge for a individual electron. So stop the video, grab a calculator, set up a simple proportion here. Cross multiply and divide. So if 1.602 times 10 to the 19th coulombs is 1 electron, 96,485 coulombs of charge would be how many electrons. That would be the mole amount. Grab your calculator, see if it's a familiar number. So this table discusses different mole relationships. It's pointing out that if we look at the formula, if we think about just having a single atom of nitrogen, it would be an AMU. But if we have Avogadro's numbers worth, then it's in grams. That works if it's a single atom, if we have a molecule, if we're looking at an atom or an ion. In each case, we're thinking about the single one has a value of AMU, and then if you have a mole's worth, it now converts it into grams per mole. Same thing if we're looking at this ionic compound of barium chloride. Conversions between these, we can go back and forth between grams and moles using the molar mass. That's what we will grab off the periodic table, and that's what we'll do again and again. We can convert between moles and formula units by using Avogadro's number. Of these two skills, we're going to be converting between grams and moles and grams almost every day in class. Very important skill for us, and that's what we would use a periodic table for. We'll do some conversions between moles and the formula unit as well. Especially important with that is to be careful and read the formula correctly. Notice within barium chloride, it's pointing out that you have within the formula, for every one barium ion, you've got 2 chloride ions. For every 1 mole of barium, you've got 2 moles of chloride. So just pointing out within this part, be careful and make sure we read the formula correctly and understand what it designates. Here's a couple calculations to give it a try. Grab a calculator, stop the video, see if you can answer these two. For the first one, I think it's a simple proportion. Molar mass is what I'm trying to find out. Molar mass is grams per mole. Within the question, I have a certain number of grams, a certain number of moles. Let's just do the math for that. So the definition of molar mass is a certain number of grams per mole. We can just do that calculation. For the second one, I think you need to do dimensional analysis for that. If you haven't given that one a try yet, please do so. Here's my setup with dimensional analysis. I've got several conversions. A certain number of grams of carbon is listed as given. Let's convert that into how many moles of carbon atoms I have, because I want to use in the formula then to see for every 2 moles of carbon, I have 6 moles of hydrogen. After this step, I'll know how many moles of hydrogen are in the sample, and then let's convert from moles of hydrogen to how many atoms. I expect it to be a large number, and sure enough it is. For more practice with the calculations, I recommend these questions. The second one in particular, I know 3.41 students oftentimes have questions with. So if you get stuck, share your answers and we'll see if we can't figure it out together.